we define the chord of a circle and examine the relation between the length of the chord and the angle it subtends at the center. In this video, we will examine the perpendicular to a chord from the center of the circle. Let's start with a demonstration. Draw a circle on a sheet of tracing paper and mark its center as O. Now, let's draw a chord AB. We then fold the tracing paper in such a way that the ends of the chord A and B coincide with each other. Then we unfold the sheet and draw a line along the crease formed when we folded the sheet. Observe that this line passes through the center of the circle and intersects the chord AB at a point. Let's name this point D. Now we know that AD and BD are of equal lengths as their endpoints A and B coincided when we folded the sheet. In other words, OD bisects the chord AB. Now if we measure the angle between OD and AB, what do we observe? It seems the line OD is perpendicular to the chord AB. So we have demonstrated that if a line segment from the center of a circle bisects the chord, the line segment is a perpendicular to the chord. Well, can we prove this mathematically? Let's start with the chord AB in a circle with center O and draw the bisector of the chord AB through the center O of the circle. From the construction, we know that AD and DB are of equal lengths. We want to examine the relationship between angles ADO and ODB. To do so, let's draw the radii OA and OB to form two triangles AOD and BOD. Now in these two triangles, AD is equal to BD as OD is the bisector. AO is equal to BO as they are both the radii of the circle and OD is common to both the triangles. So by the SSS criteria, the two triangles AOD and BOD are congruent. As angle ODA and angle ODB are the corresponding parts of congruent triangles, their measures must be equal. But AD and B lie on the same straight line. So angle ADB is equal to 180 degrees, from which we can conclude that angle ODA and angle ODB are both 90 degrees. In other words, OD is perpendicular to AB. We started with the fact that OD bisects the chord AB and proved that OD is perpendicular to AB. We can now state the following theorem. The line drawn through the center of a circle to bisect a chord is perpendicular to the chord. We can also prove the converse of this theorem, that is, the perpendicular from the center of a circle to a chord bisects the chord. Let AB be the chord of a circle with center O. Let OD be the perpendicular to the chord from the center. So if we can prove that AD is equal to DB, then it means that OD bisects AB. To do so, let's join OA and OB to form two triangles OAD and OBD. What can we say about these triangles? In these triangles, OAD and OBD, OA is equal to OB as they are both the radii of the circle. OD is common to both the triangles. And angles ADO and BDO are both equal to 90 degrees per our original assumption. Thus, by the RHS criteria of congruence, triangle ADO is congruent to triangle BDO. So from this, we can conclude that AD is equal to BD as they are the corresponding parts of congruent triangles. So this proves the fact that the perpendicular from the center of a circle to a chord bisects the chord. Let's summarize the two theorems that we have proved in this video. First, if a line through the center bisects a chord of the circle, it is also perpendicular to the chord. Then we proved that if a line through the center is perpendicular to a chord, then that line bisects the chord. That's all for this session. Keep learning, and I'll see you soon.